Collapse begins without spectacle when the iron core of a massive star can no longer sustain pressure through fusion, and in a breath of physical time gravity gains the upper hand. Electrons are captured by protons, light shatters heavy nuclei, and the core implodes until nuclear forces halt the fall at densities beyond ordinary imagination. In that violent quiet, a neutron star forms, city-sized and sun-massed, and it spins because angular momentum, like a reserved law, carries through the crisis. The newborn is hot and opaque to its own neutrinos. Convection boils through its young interior, overturning in immense cells that rise and fall while the rotation twists them into helices. In this brief furnace, a magnetic seed is lifted and folded again and again, and a dynamo is born not as a device but as a consequence of rotation and turbulence. The early field is not a single clean dipole but a tangle of geometries that coexist. Toroidal components wrap around the equator like massless girders. Poloidal lines arch from pole to pole and close beneath the crust. Smaller loops knot within and die where conductivity and heat demand it. Where neighbouring layers rotate at different rates, the magneto-rotational instability wakes and feeds on shear, multiplying small irregularities and handing them to the dynamo for further growth. In this way, the star converts differential motion into a magnetic architecture that quickly exceeds anything made in laboratories, not because the rules are different, but because scale and gravity make the same rules stronger. As neutrinos stream out and cooling begins, the first crust condenses and the motions quiet, but the field continues to strengthen while energy still resides in shear. Amplification proceeds until the reservoir of differential rotation is spent, and until convection loses force. Then the configuration begins to freeze into the solidifying layers and into the dense liquid below. Magnetic pressure already dominates gas pressure near the surface. Lines of force begin to decide where matter may move, not the other way around. Beneath a forming crust, matter slides toward unusual states. Neutrons pair and become a superfluid that carries heat and momentum in ways foreign to everyday liquids. Protons pair and become a Type II superconductor that corrals magnetic flux into thin, quantized tubes. This lesser-known but accepted detail anchors the field to microstructure. Flux tubes pinned to lattice imperfections creep under the slow push of the Hall effect and relax by resistive processes over long stretches of time, so that a field that bursts into strength within seconds now evolves in drawn-out, murmuring centuries. The crust tries to hold the shape the field prefers. The field tries to follow the paths the crust permits. The compromise is slow drift. Facts and uncertainties share the same room. It is well grounded that collapse, rotation of only a few milliseconds, and deep convection can drive a dynamo to magnetar scale. It is also reasonable that part of the field is a fossil, a remnant of the progenitor star's interior magnetism compressed and concentrated as the core shrinks. The balance between these sources remains unsettled, and a quiet mystery persists in the population itself. Only a minority of neutron stars carry fields above 100 trillion to 1 quadrillion Gauss, and no single threshold cleanly predicts which newborns will join that company. Metallicity, mass loss in stellar winds, rotation history, and companionship in binary life all appear as influences. None explains the full pattern. Seen from outside, the newborn object already shapes light. In fields this strong, the vacuum behaves like a medium and rotates the polarization of photons, a prediction of quantum electrodynamics that becomes visible near these stars. The magnetosphere that hardens around the surface decides where particles can move and will later guide the soft gamma repeater behavior that gives magnetas their name. For now it is a rigid cage that enforces co-rotation and cleans nearby space of free matter, The energy density stored in the field exceeds any thermal store remaining in the atmosphere. So the geometry of the field, not the temperature of the gas, dictates the immediate future. Three soft ironies settle into place without asking for attention. The strongest magnetic fields in the known universe are born in one of the smallest volumes, as if space needs less room to do work. The field that will later tear the crust into starquakes begins as a balm that suppresses chaos and carries away energy. The phenomenon that may appear as a brief, violent flare is sustained by processes so gradual that they count themselves in centuries. A gentle analogy suggests itself with human industry, an assembly line that, in its first hour, installs the very bracing that will later limit motion. There is no climax in this beginning, because the process tends toward rest. A magnetar is not declared, it is prepared. Amplification approaches a plateau as the dynamo exhausts differential rotation and convection weakens while neutrinos escape, and the field freezes more tightly into the forming crust and the superconducting core. The dipole reaches above 100 trillion to 1 quadrillion Gauss, and interior toroidal stores may exceed even that. Yet outside there is only the slow breathing of cooling and the persistent turn of rotation. Nothing closes here. The star cools, the rotation eases, the geometry stiffens, and the foundations of a magnetar settle into place. The processes do not finish. They trade speed for silence. Crustal fractures, giant flares, and polarized light that turns as it travels will later find their source in this early hour, when turbulence becomes order and order becomes memory. For now the object turns in the dark, and the field it has built holds space like an invisible architecture, quiet and immense. The crust of the newborn neutron star thickens into a lattice of ions embedded in a sea of electrons, a structure that resembles no earthly metal, yet functions as one of the strongest solids known. Above it lies a magnetosphere already shaped by the frozen magnetic field, while beneath it, the superfluid neutrons and superconducting protons create states of matter that laboratory physics can only approach by analogy. The surface, though only a few kilometers across, radiates X-rays as it cools from hundreds of billions of degrees toward calmer temperatures, and in that radiation the first signals of magnetar identity escape. Within this setting, the magnetic field does more than persist. It begins to rearrange. Flux tubes in the superconducting core pin themselves to the lattice of the crust, and as the star continues to lose rotational energy, those tubes experience tension and must slowly migrate outward. The motion is resisted by imperfections, so the system stores stress that accumulates until it finds a path of release. The Hall effect, a process where currents drift under the influence of the magnetic field itself, becomes important. Electrons slide sideways in response to the fields they carry, creating small currents that twist the larger geometry. What appears smooth from a distance is internally restless, always adjusting to balance competing demands of rotation, pressure, and magnetic structure. This fact, established by detailed models and supported by observations of magnetar activity, shows that these stars are never static even when no bursts are visible. A lesser-known detail lies in the photon environment. In fields stronger than 10 to the 14th Gauss, the vacuum behaves not as emptiness, but as a birefringent medium. Light polarized in one direction moves differently than light polarized in another. A quiet exhibition of quantum electrodynamics made real. When astronomers measure the polarization of X-rays from magnetars, they watch vacuum itself behave like a crystal, bending light without substance. This subtle effect, invisible in weaker fields, turns the surrounding emptiness into an active player. A mystery persists in how this field maintains such intensity across millennia, Theoretical resistive decay should erode it, yet observations show that some magnetars remain active for tens of thousands of years. Perhaps internal toroidal fields hidden beneath the crust serve as reservoirs that feed the observable dipole. Perhaps the balance of superfluid vortices and superconducting flux tubes prolongs the lifetime by pinning energy into structures that drift only reluctantly. No clear consensus resolves the timescale puzzle, and so the question lingers like a low tone. There are ironies here that rest gently against the scientific frame. The same electrons that once fused with protons to create neutrons now flow as currents that preserve magnetic strength. A star collapsed to silence continues to speak through bursts of X-rays that flash across galaxies. The crust, only a kilometer thick, holds back stresses capable of tearing itself apart, proving again that fragility and strength can be the same property. If one seeks a modern analogy, the magnetar behaves like a vast battery, charged in seconds by collapse and discharging over ages, but unlike human devices, it cannot be disconnected from its own structure. The crust and the field are partners in constraint. Starquakes occur when magnetic stresses surpass what the lattice can bear, and the sudden fracture changes the external field, accelerating particles and sending radiation outward. Yet between such events the magnetar is not loud but subdued. It turns steadily, slowing under the torque of its own magnetism. Each rotation loses a fragment of energy, and that gradual spin down offers astronomers a measure of the field itself. By timing the pulses of emitted light, scientists infer strengths that theory predicted but no earthbound machine could verify. The strongest known magnets do not require assembly lines, coils, or power supplies. They require gravity's collapse and nuclear matter. Over long intervals, the Hall drift continues to shuffle currents sideways, redistributing magnetic energy within the crust. Where gradients sharpen, resistive dissipation warms the interior, providing a heat source that explains why magnetars shine more brightly in X-rays than ordinary neutron stars of similar age. Thus the field both cools and warms, a contradiction that holds true without strain. Energy leaves through radiation, yet energy is also released from the rearrangement of the field itself. As centuries pass, the geometry outside simplifies toward a dipole, while inside complex knots remain, unseen but crucial. It is this hidden reservoir that may later feed giant flares, sudden releases that dwarf the ordinary output of stars. The mystery deepens because only a few dozen magnetars are known, though the galaxy must contain far more neutron stars. Do most die quietly before their fields become observable, or do we simply fail to notice them until they burst? The answer is unsettled. Observational selection, birth conditions, and evolutionary pathways all contribute to the uncertainty, leaving the census incomplete. The silence between known magnetars may hold more than absence. Three more ironies rest with quiet weight. The same collapse that creates a solid lattice also seeds its inevitable failure. The greatest source of order in the star, its magnetic field, is also the source of its most violent irregularities, and the very mechanisms that slow the rotation, draining kinetic energy, also preserve the field by preventing rapid dissipation. These contradictions do not need resolution. They coexist like layers in the crust itself. The passage of time offers no narrative but only persistence. The star spins more slowly. The crust adjusts to stresses. The field drifts through rearrangements too slow for human timescales, but decisive in astrophysical terms. When viewed across thousands of years, these motions amount to sculpting, as if the star is shaping its own environment with invisible chisels of magnetism. There is no climax, only endurance, Magnetars produce their fields not through one act, but through ongoing dialogue between collapse, quantum states, and crustal response. The process is patient, measured in centuries of subtle change. The evidence is written in polarized light, in X-ray luminosity beyond expectation, in sudden bursts that echo across galaxies, and in the slow timing of rotations that lengthen like the measured breathing of a sleeper. All of it rests on the invisible architecture established in the first seconds of collapse, sustained through processes that do not seek our notice but continue regardless. In this quiet second stage, the magnetar does not add to its field but learns how to live with it, and the universe accepts this balance without hurry. The magnetar now exists not only as a remnant of collapse but as a laboratory of extreme physics that unfolds in silence. Its spin slows steadily, the once millisecond rhythm elongating as magnetic braking drains rotational energy. Yet even as the outward rotation declines, the internal field continues to dominate structure. Field lines arc from pole to pole, linking surface to magnetosphere, while hidden toroidal components press sideways beneath the crust like invisible girders that refuse to relax. In this balanced contest between solid and field, the star establishes a dynamic state that astronomers call stability, yet is in truth a slow dance of tension and drift. Each year that passes carries away rotational energy in electromagnetic radiation and in the acceleration of particles along open field lines. The loss is calculable, observable, and provides the direct evidence that the field is indeed of magnetar scale. Timing of pulses, when visible, shows a spin down far steeper than in ordinary pulsars. The energy loss is not catastrophic, it is incremental, steady, like a candle that burns slower than expected yet never brightens. This fact is accepted in astrophysical models and has been confirmed through decades of measurement. Yet even here a quiet detail emerges. The observed slowdowns are not perfectly smooth. Glitches occur, sudden small accelerations that remind us the interior is superfluid, and that vortices pinned to the lattice sometimes unpin en masse, transferring angular momentum abruptly. The consequence is paradoxical. The most rigid stars slip, and in their slips they reveal the properties of fluids that no human can bottle. Such events, though subtle, are frequent reminders that magnetars live not in quiet equilibrium, but in continual compromise. A lesser-known real-world detail arises in the radiation itself. In fields of this magnitude, electrons and positrons populate the magnetosphere in pairs created by the fields themselves. These particles spiral along magnetic lines, emitting X-rays through curvature radiation and inverse Compton scattering. The effect fills the surrounding space with a halo of high-energy light that persists even in quiescent phases. Observations from space telescopes reveal this as persistent X-ray emission, brighter than theory once predicted, and it forces astrophysicists to recognize that the magnetic field is not merely static architecture, but an engine that stirs the surrounding vacuum into action. The quiet mystery here remains why some magnetars release giant flares, while others of seemingly similar field strength remain calm. The December 2004 flare from SGR 1806-20 released more energy in fractions of a second than the Sun radiates in hundreds of thousands of years, yet its peers have not repeated the act. The triggers are debated: crustal fractures, reconnection in twisted magnetospheres, hidden instabilities in toroidal reservoirs. No model captures the diversity fully, and so uncertainty lingers like background noise that never resolves into clarity. The ironies deepen as understanding grows. The field that restrains particles into clean paths also unleashes bursts that scatter photons across galaxies. The stability of rotation is interrupted by glitches that come from the very superfluidity thought to preserve balance, and the silence of empty space becomes a medium that bends and splits light because the field is too strong to ignore. If one seeks analogy, it is like a clock whose gears bend time while trying to keep it, ticking steadily yet with hidden jolts that no watchmaker intended. The magnetar continues to cool as neutrino emission subsides, yet its surface remains hotter than ordinary neutron stars, warmed from below by dissipation of magnetic energy. This paradox ensures that they remain visible long after similar-age stars fade into quiet radio silence. The Hall drift keeps currents alive within the crust, and resistive decay transforms magnetic tension into heat. The cooling and heating balance to create an object that glows stubbornly brighter than its peers, another contradiction folded into the quiet life of the magnetar. Over thousands of years, the dipole field gradually weakens but does so unevenly. Certain regions of the crust carry stresses longer than others, and when they yield, the release of energy propagates outward in Alfvén waves that jolt the magnetosphere and accelerate particles violently. These events are not predicted by calendar, they occur in silence until they erupt without warning. Yet between them, centuries can pass with no spectacle, only the slow adjustment of fields within solid and fluid. For astronomers, these intervals are as important as the bursts, for they reveal the baseline, the enduring presence of extraordinary magnetism, even when nothing dramatic occurs. Another detail that rests with little notice is the alignment of fields. Some magnetars show evidence that their magnetic and rotational axes are misaligned, producing irregularities in pulse profile and polarization. This simple geometry decides how observers on Earth perceive them and whether they are recognized at all. Many may exist unseen simply because their beams do not sweep across our line of sight, leaving us with an incomplete census. The ironies return softly. The field that should decay quickly persists, the superfluid that should glide smoothly glitches, and the beams that should signal uniformly instead blink in uneven rhythms. These contradictions are not errors but natural consequences of physics at limits we rarely encounter. The magnetar remains indifferent to whether it is observed. Time passes without climax. The field rearranges at the pace of crustal drift. The spin slows fractionally each year. Glitches arrive without pattern. Bursts may or may not occur. All the while, the object endures, and the processes that sustain its field continue unbroken. The story has no turning point because it is not a story but a condition, one that endures as long as magnetic energy outweighs dissipation. The magnetar does not produce its field in an instant. It maintains and reshapes it through quiet tension, through compromises between solid crust and superconducting core, through the drift of currents that never find final rest. The human mind may prefer drama, but the universe offers persistence instead. In the deep silence of space, the magnetar turns, glowing more fiercely than its age should allow, carrying within it the paradox of order born from collapse and strength held in fragility. The process is not resolved here. It stretches into further ages where field, crust, and core will continue their dialogue unseen. As millennia pass, the magnetar continues to age in ways that defy familiar measures. Its rotation slows under the relentless torque of its immense magnetic field, and each turn becomes a little longer, a little weaker, until the rhythm that once measured milliseconds now lingers in seconds. Yet this slowing does not extinguish the presence of the field. Instead, it reveals its endurance, a persistence of structure far outlasting the initial dynamo that created it. The crust thickens and cools, contracting into a lattice that is harder and more brittle than before, and within this lattice stresses build where magnetic lines of force demand shifts that the solid cannot easily grant. These stresses accumulate like invisible tectonics until sudden fractures, known as starquakes, release the pent-up energy in jolts that reverberate through the magnetosphere. Observations of soft gamma repeater outbursts confirm this process, each burst lasting mere fractions of a second, but carrying more energy than many suns emit in a year. The fact of crustal fractures under magnetic strain is well established, and their consequences are seen across the galaxy whenever a magnetar briefly outshines everything around it. A lesser-known detail is the subtle prelude. Even before a quake occurs, the crust groans under magnetically induced shear, producing heat that leaks through the surface as excess X-ray luminosity. Sensitive telescopes catch this glow, offering a glimpse of tension long before it breaks. It is as though the star whispers its unrest through photons before shouting through gamma rays. Yet mysteries endure. Not all stresses break with bursts, and not all bursts follow from visible build-up. Some magnetars remain quiescent for centuries, then erupt without warning. Why some fractures cascade into giant flares while others dissipate quietly remains unsettled. Perhaps geometry decides, with toroidal fields storing deeper reservoirs that only occasionally connect to the surface. Perhaps the trigger lies in subtle rearrangements of flux tubes within the core. No consensus has closed the question, and the uncertainty is part of the magnetar's identity. Three ironies emerge as one contemplates this stage. The most rigid crusts are the ones that fail most spectacularly. The fields that imprison matter in perfect order also tear the star apart from within. And the calmest long periods of silence are the ones most likely to precede sudden violence. These contradictions lie quietly within the physics, not as drama but as symmetry. The magnetosphere itself responds to these stresses with quiet preparation. Twisted by crustal movement, it stores energy in currents and in distorted field lines, and when reconnection occurs, the magnetosphere releases bursts in patterns reminiscent of solar flares, but magnitude stronger. The analogy to the sun is tempting but incomplete. For magnetars carry fields so strong that quantum electrodynamics modifies even the propagation of photons. In this environment, pairs of particles are ripped from vacuum and guided along field lines like dancers compelled by a silent partner. Such processes turn empty space into plasma without need for external supply. A modern analogy might liken the magnetar to a power grid that not only carries currents, but manufactures its own charge carriers continuously. The mystery deepens when considering longevity. Magnetic decay should smooth the field into weakness within tens of thousands of years, yet observations show active magnetars persisting beyond that timescale. Some theories propose hidden interior toroidal fields, orders of magnitude stronger than the visible dipole, locked beneath the crust and leaking energy gradually. Others suggest that coupling between the crust and the core preserves energy in slow drift, rather than allowing rapid decay. None explain fully why some magnetars flare long after they should have cooled into quiet remnants. The contradictions sit unresolved, like stones unturned on a silent plain. Between outbursts, the magnetar lives in endurance. Its surface emits persistent X-rays, brighter than neutron stars of comparable age. This excess cannot be explained solely by cooling. Instead, the crust itself releases heat from the slow rearrangement of currents, the resistive decay of stresses, and the Hall drift that moves magnetic energy into smaller scales where it dissipates as warmth. Thus, the magnetar sustains its glow by consuming its own field. Irony again. The very strength that defines it is also the source of its slow erosion. From afar, this process is not visible in moments, but in centuries. The star glows, pulses fade, flares erupt occasionally, and then time continues without event. To human perspective, these stars appear restless. To cosmic timescales, they are steady, persistent, and patient. The magnetar produces its field not as a one-time phenomenon, but as a continuing negotiation between structure, crust, and quantum matter. Each adjustment is another step in this endless balancing act. There is no sense of completion, no conclusion. Instead, there is only drift, fracture, release, and endurance. The magnetar remains an unresolved presence in the universe, turning slowly, glowing steadily, breaking rarely, and reminding observers that strength and fragility are bound together. A final irony rests here as well. These stars, born in catastrophic collapse, find their true identity not in that explosion, but in the slow, quiet processes that follow. The loudest moment of their lives is not the one that defines them. It is the enduring silence afterward, the persistence of magnetic fields that no machine can rival, the slow dance of crust and core that continues without conclusion. In the absence of drama, the magnetar writes its history in quiet endurance. The magnetar advances into ages measured not by centuries but by tens of thousands of years, and still its magnetic presence dominates its existence. The once violent collapse has long faded into silence, yet the energy stored in the field continues to guide every process. The crust has thickened and hardened, a kilometre of crystalline matter suspended above a superfluid sea, and within this rigid skin tensions build in slow increments. Each rotation, now reduced to several seconds, leaks energy into the surrounding space. Spin down is not dramatic, but each fractional loss of momentum is a record of the immense torque applied by the magnetic field. Astronomers on Earth measure these changes through careful timing, noting that the rate of deceleration remains orders of magnitude higher than in ordinary pulsars. This fact, well established, demonstrates that the field retains its staggering strength across eras that exceed the lifespans of civilizations. A lesser-known detail is how the magnetar influences its environment beyond the crust and magnetosphere. Its strong magnetic dipole can sweep surrounding interstellar plasma, creating cavities and bow shocks as the star drifts through space. The wake carved into the medium is invisible to the eye yet measurable in radio and X-ray signatures, and it reveals that magnetars sculpt their local regions as they travel, leaving traces of their passage across parsecs. This is not the chaos of a flare but the quiet persistence of influence. A mystery continues in the distribution of magnetars across the galaxy. Only a few dozen are catalogued, despite theoretical predictions that thousands should exist. Perhaps many remain hidden, their beams never aligned with Earth. Perhaps their flares are rare, and without them they blend into the background of ordinary neutron stars. Or perhaps the conditions that form magnetars are far rarer than models suggest. The absence itself is data, yet it refuses to resolve into certainty. Three soft ironies arise in this stage of life. The most powerful fields in the galaxy can only be recognized by their absences: cavities in plasma, gaps in pulses, sudden silences that mark unseen flares. The stars that embody extremity in physics are often invisible unless they fracture, making their violence the only signal of their presence. And the processes that last longest are the ones least often noticed, their steady emissions drowned in the background hum of the cosmos. A modern analogy may help. The magnetar is like a dam that leaks not in torrents but in steady drips. The wall remains immense, the reservoir vast, but over centuries the small releases accumulate into rivers that alter entire valleys. The field is not released all at once. It is spent gradually, quietly, in ways that shape environments without spectacle. The crust beneath this dam remains under constant strain. Starquakes occur less frequently as the star cools and stiffens, but when they do occur, they can be even more severe, for accumulated stress has had longer to grow. Observations of giant flares show that some events occur long after the birth of the magnetar, with energies that suggest deep interior toroidal fields still feeding the surface. These unseen reservoirs may persist for tens of thousands of years, reinforcing the idea that the magnetar is not a transient state but a long-lived identity. Yet uncertainties deepen here. How long can such reservoirs last before decay reduces the star to an ordinary neutron star? Models suggest hundreds of thousands of years at most, but observations remain sparse, and the true lifetime of magnetar activity is unsettled. The question lingers like a pause that stretches without conclusion. In the meantime, the magnetar continues to affect its surroundings. Its radiation ionizes nearby gas, and its wind shapes cavities. Its bursts, when they occur, send gamma rays that can be detected across galaxies, and occasionally even across the observable universe. Yet between these events it remains silent to most instruments, a faint X-ray glow that only the most sensitive telescopes can detect. The contradiction is clear. A star of immense power spends most of its life in quietude, revealing itself only in rare moments of sudden release. The ironies continue. The crust that hardens with age also becomes more brittle, increasing the severity of each fracture. The spin that slows steadily continues to power emissions long after intuition would suggest exhaustion, and the deeper the field hides in the core, the longer it can persist, sustaining activity long past the point at which surface evidence should have faded. These are not paradoxes in need of resolution, but harmonies of physics expressed at unfamiliar scales. The passage of time does not change the magnetar's essence. It remains a neutron star shaped by collapse, defined by magnetic extremity, sustained by quiet processes that unfold over epochs. Its future is not a sudden ending but a slow fading, a long decline of field strength, spin and luminosity. Yet the decline is so gradual that it appears as endurance. Observers may count the years of activity, but for the magnetar itself there is only persistence. The processes continue whether or not they are seen. The field drifts, the crust strains, the spin slows, the emissions flicker, and the silence dominates. In this stage, the magnetar becomes not a transient firework, but a constant ember, glowing faintly yet shaping its environment with every turn. It endures, and in endurance it defines itself. The magnetar drifts further into time, carrying its vast magnetic inheritance across a galaxy that scarcely notices its passing. Its rotation, now counted in several seconds, continues to slow, each pulse stretched longer by the drag of its own field. Yet despite this deceleration, the field lines remain taut, arching outward into the magnetosphere, enclosing space in an invisible cage. The crust beneath them endures unrelenting stress, storing energy in its lattice like a bow drawn too far, waiting for the inevitable moment of release. The fact of this process is beyond dispute. Crustal fractures, confirmed by bursts of high-energy radiation, show that magnetic fields of quadrillion Gauss magnitudes are not merely abstract numbers, but active forces that shape the star's existence. A lesser-known detail lies in the aftershocks of these quakes. Following major outbursts, astronomers have observed gradual tails of X-ray emission, decaying over days or weeks, as if the crust continues to shift and settle long after the initial fracture. These lingering echoes suggest that the star itself rings with energy, resonating like a bell struck by forces invisible to the eye. Such observations refine the understanding of magnetar activity, revealing not a single violent moment, but a sequence of adjustments that carry on quietly in the dark. Yet mysteries remain as deep as ever. The exact mechanism that triggers giant flares is not agreed upon. Some models propose reconnection events in the magnetosphere, akin to but far stronger than solar flares. Others emphasize internal toroidal fields releasing stress into the crust. Still others suggest interactions between superfluid vortices and magnetic flux tubes in the core. The truth may combine all of these, or may be something yet undiscovered. This uncertainty persists despite decades of observation and theory, reminding us that magnetars remain laboratories of physics beyond our full reach. Ironies return with quiet persistence. The most extreme bursts are born not from chaos but from order, too rigid to bend until it breaks. The brightest high-energy events in the sky arise from stars that spend most of their existence in silence, and the same field that forces matter into disciplined alignment also guarantees that alignment will never remain stable. A modern analogy offers itself in the quiet hum of a power line stretched across a valley. For days it carries current without notice, but when a storm shifts its balance, the line snaps with a report that echoes across the hills. The magnetar is such a line, scaled to cosmic dimensions. Over long stretches of time, the magnetar reshapes even its external environment. The outflows of energy and particles carve bubbles in the interstellar medium, sometimes leaving behind faint nebulae detectable in X-ray and radio bands. These ghostly halos bear witness to activity centuries or millennia past, their faint glow a memory of fields once freshly tangled. In this way, the magnetar writes a history in the surrounding gas, etching signatures that outlive individual bursts. This fact links the interior struggles of a star to the broader canvas of its galaxy, a reminder that even silence leaves marks. A deeper mystery persists in the diversity of behavior. Some magnetars flare frequently, releasing dozens of bursts in short intervals, while others remain dormant for centuries. The reason for this difference remains unsettled. Variations in internal structure, magnetic geometry, or initial conditions of formation may be responsible, but no definitive pattern explains the observations. Each magnetar seems to follow its own rhythm, as though the universe allows many solutions to the same equation. Irony lies again in this diversity. The stars most defined by their fields refuse to be uniform. They demonstrate that even in the realm of extremity, variety persists, and no single template governs their lives. The passage of time does not relieve these contradictions. Instead, it deepens them. As the magnetar ages, its surface cools further, yet internal heating from magnetic rearrangements keeps it luminous in X-rays. The field decays slowly, but not evenly. Some regions weaken faster, others maintain hidden strength, and the balance between them changes over millennia. This unevenness ensures that stresses never fully vanish. The crust continues to resist and then to yield, the magnetosphere continues to twist and then to relax, and the cycle continues without resolution. Observers, measuring from afar, record pulses, bursts and spectra, but the processes themselves unfold in silence, indifferent to attention. The star endures, not as a spectacle but as a condition. 3 more ironies rest here like faint embers. The most powerful magnets in the cosmos require no energy input beyond their own structure, yet they consume themselves in sustaining that strength. The most violent flashes of radiation are born from processes too slow to notice until they erupt, and the most extreme stars, products of collapse and catastrophe, spend most of their lives fading in obscurity, their glory hidden in patience rather than spectacle. In this long stage, the magnetar demonstrates not climax but persistence. Its field drifts, its crust strains, Its spin slows, its light flickers, and yet nothing resolves. It does not collapse further, it does not flare continuously, it does not fade entirely. It simply endures, caught between processes that cannot finish. The magnetar produces its powerful magnetic fields not in one moment but across eons, through the steady compromise of forces that never yield. This compromise is its life, in silence, in endurance, in contradictions unending. The magnetar continues to exist, turning slowly in the dark, shaping its environment with fields unseen yet immense, and embodying physics at its most extreme without ever requiring drama to persist. The magnetar continues its existence as a paradox of silence and power, turning slowly with a rhythm that now stretches across several seconds, while still holding within it fields that could strip atoms apart. The rotational energy diminishes further, yet the star remains luminous, not because of its spin, but because of the gradual release of magnetic stress from within. This fact is confirmed by the persistent X-ray glow that marks magnetars even in their quiet phases. Where ordinary neutron stars of similar age cool and fade into invisibility, magnetars remain visible because their fields refuse to rest. This persistence is not a single phenomenon, but a collection of processes. The Hall drift in the crust continues to shuffle currents sideways, turning large-scale order into finer knots that then decay resistively. Each knot warms the crust a little, each release contributing to a steady output of photons. It is a process that does not announce itself with noise but with constancy, an ongoing conversion of magnetic energy into thermal light. A lesser-known detail emerges in the polarization of this light. Recent measurements show that X-rays from magnetars are highly polarized, as if aligned by invisible rails. This arises because the vacuum around them is birefringent, splitting light into modes that travel differently depending on orientation to the field. Observing such polarization offers not only confirmation of theory, but a glimpse into conditions impossible to recreate on Earth. In this way, magnetars become laboratories of quantum electrodynamics, their very silence carrying experiments across the cosmos. Yet mysteries deepen in the details. Why do some magnetars show clear periodic bursts while others remain unpredictably quiet? Why do fields of similar inferred strength produce such different outcomes in terms of flare frequency and energy? Theories attempt to connect these differences to hidden toroidal components or variations in the superconducting core, but no consensus satisfies the evidence. The uncertainty lingers, as if the magnetar's own silence resists translation into human clarity. Irony sits quietly here. The strongest physical fields in the universe appear as silence when they're most stable. The same vacuum once thought empty becomes an active medium, bending light as if it were crystal. And the stars most luminous in bursts are otherwise among the faintest, their brightness appearing only in rare instants. A modern analogy presents itself in a mountain range under snow. Most of the time the slopes lie still, the snowpack silent and unbroken. Yet beneath the surface, layers shift and compact, and once in a while an avalanche cascades down, visible for a moment but born of processes long concealed. The magnetar is such a mountain, its avalanches written in photons instead of snow. Over greater spans of time, the magnetar's environment also reflects its presence. The wind of particles accelerated along field lines escapes into interstellar space, producing faint nebulae that glow in high-energy light. Some of these nebulae show arcs and shells that betray episodes of past flaring. In this way, the magnetar leaves behind footprints of events long past, traces of energy spread across parsecs. Observers interpret these structures as relics of episodes too distant in time to witness directly. The magnetar thus becomes not only a star but a historian, recording its own activity in the gas around it. Another mystery persists in the fate of these fields. Calculations suggest that magnetic energy should decay over hundreds of thousands of years, but the evidence of persistent brightness in older candidates challenges this. Perhaps deep reservoirs remain locked beneath the crust, toroidal fields that only slowly unwind. Perhaps interactions between vortices in the neutron superfluid and flux tubes in the superconducting protons prolong the lifetime. The physics of such interactions is still being unravelled, and until it is settled, the question of how long a magnetar can remain active remains unanswered. Three more ironies reveal themselves. The very processes that cool the star, neutrino emission and photon radiation, are offset by heating from magnetic rearrangement, so the star cools and warms simultaneously. The crust that prevents collapse also ensures fractures, a structure that both stabilizes and destabilizes at once, and the bursts that reveal magnetars to us destroy our ability to see them steadily, overwhelming instruments with brilliance for moments before leaving only faint glows. The magnetar persists in its contradictions. Time continues without resolution. The spin slows further. The field rearranges gradually. The crust endures and yields in turn. There is no final event, no climax to announce closure. Instead, there is endurance, processes that continue whether or not they are observed. The star does not require witnesses. It continues its dialogue between matter and field, between rigidity and release, between silence and sudden light. It is not a drama, but a condition, a state that persists because it cannot do otherwise. The magnetar produces its magnetic fields not as a singular act, but as a sustained negotiation between gravity, quantum states, and the resistance of matter under strain. That negotiation is the magnetar's life, and it unfolds in silence, far removed from human measures of time, indifferent to our attempts to turn it into story. The magnetar advances deeper into its lifetime, its rotation now stretching to many seconds, a slow and deliberate turning that contrasts sharply with the furious birth it once endured. The magnetic field remains unimaginably strong, but its visible influence has changed. Bursts become rarer, persistent emission continues, and the star enters an era defined not by spectacle, but by endurance. The fact of its longevity is accepted. Observations confirm magnetars tens of thousands of years old, still glowing with excess X-ray luminosity. The star should have faded, but it resists, its magnetism prolonging its visibility beyond expectation. A lesser-known detail lies in the spectral lines observed from its surface. In such fields, atoms are deformed, their electron clouds elongated and compressed, producing unusual line features in the emitted light. These distortions are not artifacts of observation, but genuine consequences of physics under duress. Thus, even the simplest element, hydrogen, behaves strangely, reminding us that matter itself is rewritten in the presence of fields this strong. The unresolved mystery lies in why magnetars exist at all in such small numbers. If massive star collapse often produces neutron stars, and if dynamos can amplify fields to quadrillion Gauss strengths, why do only a few % become magnetars? Theories suggest progenitor mass, rapid rotation, and metallicity as factors, but the precise recipe is uncertain. It may be that subtle variations in collapse dynamics, invisible to observation, decide the outcome. This mystery endures because the sample is small and the process is hidden. Soft ironies accompany this stage. The stars defined by extremes are counted in dozens, their rarity contrasting with their strength. The very fields that rewrite matter also ensure that the objects carrying them are difficult to understand. And the most enduring magnetaires may be the least noticed, their activity subdued, their light faint, their power hidden in silence. A modern analogy might be a library containing volumes of the rarest texts, locked behind doors few can open, their contents vast yet unread. The magnetar is such a library, storing secrets in its crust and core that may never be fully revealed. Over time, the magnetosphere continues to shift. Twists in the field accumulate from slow drift within the crust, and occasionally they relax in bursts of reconnection. These events may not reach the violence of giant flares, but they still release energy measured across parsecs. Instruments detect them as sudden, short X-ray bursts, faint compared to the grandest events but still exceeding anything the sun has ever produced. Between these outbursts, the magnetar glows faintly, its photons polarized, its spectrum shaped by physics far from human scales. The cycle of stress and release repeats without conclusion. Another subtle effect occurs in the interior. The neutron superfluid, threaded by quantized vortices, continues to interact with the superconducting proton flux tubes. When vortices migrate, they can drag flux tubes with them, slowly rearranging the field within. These microphysical interactions are unseen, but their macroscopic consequences include glitches in rotation, sudden adjustments in spin that reveal the fluid dynamics within. The irony lies in scale. Events governed by quantum rules manifest as stellar phenomena visible across the galaxy. The crust, though hardened further, remains under strain. Each quake injects energy into the magnetosphere. Each fracture alters the distribution of currents. But the star itself does not break. It adjusts, heals, and continues. This resilience ensures that magnetars remain active across epochs, never steady, never finished, but always persistent. Mysteries deepen still. Do magnetars eventually lose their identity, fading into ordinary neutron stars once their fields decay sufficiently? Or do they carry remnants of their magnetism forever, invisible yet distinct? Observations cannot yet answer, for the timescales exceed recorded history. The universe carries the answer silently, while we watch only fragments. Irony speaks again. The stars that challenge theory most are the ones we see least often. The objects that reshape matter itself exist in obscurity, while lesser stars dominate our night sky. And the processes that could answer our questions require timescales far longer than the span of human study. These truths do not frustrate the magnetar. They define it. Time drifts onward. The spin slows further, but never to a halt. The field rearranges, but never to disappearance. The crust strains, but never to collapse. Each process reaches toward conclusion, but never arrives. This is the nature of the magnetar, to persist in tension, to exist in unresolved balance, to embody physics stretched to its limits without ever escaping its own contradictions. The magnetar produces its powerful fields not through a single act, but through centuries of compromise between matter, rotation, and magnetism. It remains a star that never finishes becoming what it is, and in that persistence lies its identity. The magnetar moves further into its middle age, if such a term can be applied to an object that measures its existence in tens of thousands of years. Its rotation, now reduced to languid periods of several seconds, is no longer a reservoir of meaningful energy, yet the star persists in radiance. The brightness comes not from spin, but from the gradual surrender of magnetic energy, stored deep within its crust and core. This steady emission distinguishes magnetars from their quieter neutron star kin, and it remains one of the clearest signatures of their identity. The fact is plain. telescopes consistently record magnetars glowing more brightly in X-rays than expected for their age, confirming that their magnetism is not merely a static property, but a continuing source of heat. A lesser-known detail is that even in their silence, magnetars influence the polarization of background light passing near them. Their strong fields bend photon paths and alter polarization states of distant starlight and background radiation. These subtle distortions offer indirect evidence of their presence, like ripples in water that betray a stone lying beneath the surface. Such faint influences remind us that the reach of their fields extends well beyond their crusts, shaping not just their own emission, but the passage of light through nearby space. Yet mysteries endure. The ultimate fate of a magnetar's field remains unresolved. Will the toroidal stores in the core eventually unwind entirely, leaving behind an ordinary neutron star, or do remnants of the field linger indefinitely, unseen yet still immense? Observational data remain incomplete, and theoretical models disagree on decay timescales, ranging from hundreds of thousands of years to millions. This uncertainty underscores how little of a magnetar's true lifetime has been observed, for human eyes and instruments have only glimpsed a thin slice of their chronology. 3 ironies arise quietly. The most powerful magnetic fields known fade into invisibility before their full story can be traced. The stars that hold the greatest strength are reduced in time to anonymity, indistinguishable from their weaker brethren, and the very processes that make them remarkable also hasten their decline, consuming their energy to maintain their glow. A modern analogy suggests itself in a torch fueled by its own structure. It burns not by adding external fuel, but by slowly consuming its own body, glowing brighter than others for a time, but ensuring its eventual dissolution. The magnetar is such a torch, burning its magnetic skeleton into light. Over these long intervals, the magnetosphere also evolves. Twist accumulate as crustal motions shift footpoints of field lines. When the stress grows too great, reconnection occurs, releasing energy in bursts. Some are minor, detectable only by sensitive instruments, while others can be vast, outshining entire galaxies for brief moments. These flares are reminders that the apparent silence hides immense reservoirs of energy. Yet between them, the magnetar spends most of its life in endurance, quietly luminous, seemingly calm. Another subtle process is the gradual coupling of the superfluid core to the crust. As the star cools further, superfluid vortices interact more strongly with proton flux tubes, adjusting the interior dynamics of rotation. Glitches, once relatively frequent, become rarer but sometimes larger, as long-stored angular momentum is suddenly transferred. These events confirm that even deep inside, long after birth, the magnetar remains restless. The irony is sharp. The colder the star becomes, the more brittle its behavior, and the rarer but more dramatic its adjustments. Mysteries remain in the diversity of behavior. Some magnetars continue to flare energetically for tens of thousands of years, while others fade quietly after only a few thousand. The cause of this variability is not resolved. Progenitor mass, initial spin, and field geometry may contribute, but no model fully explains the differences. Each magnetar remains a unique case study, refusing to conform to a universal pattern. Another irony lies in the way they challenge predictability. The most extreme physical conditions do not produce uniformity, but variety, suggesting that extremity itself breeds divergence. Observers note the gradual decline of surface temperatures, yet magnetars remain hotter than models predict. The persistent heating from magnetic decay ensures that they continue to shine, even as ordinary neutron stars of similar age fall into silence. This stubborn brightness is not a defiance of physics, but a consequence of it, a slow revelation of the vast energy stored in magnetism. The contradiction is gentle. Cooling and heating occur simultaneously. Decay and persistence coexist. Silence and bursts alternate without resolution. In this stage, the magnetar embodies endurance without closure. It continues to spin, though slowly. It continues to emit, though faintly. It continues to flare, though rarely. Each process persists without end, never concluding, never exhausting itself entirely. Three final ironies settle softly here. The stars that shine brightest in rare moments spend most of their lives unseen. The most violent bursts in the sky arise from objects defined by patience, and the processes that seem to hasten decline ensure continued visibility, delaying the silence that would otherwise follow. The magnetar exists as a paradox stretched across time. It produces its magnetic fields not as an instant of creation, but as an ongoing state of being. A compromise between quantum matter and cosmic gravity, a dialogue that does not finish. In the quiet depths of space, the magnetar persists, turning slowly, glowing faintly, shaping its surroundings in ways unseen, carrying contradictions into ages that outlast any measure of human history. The magnetar continues into still deeper epochs, its light a steady whisper across the void, its rotation a languid measure of time that now stretches toward 10 seconds or more. The energy of its spin has long been exhausted as a meaningful driver, and yet it remains visible, glowing in X-rays and occasionally bursting in flashes of high-energy light. The explanation lies not in motion, but in magnetism, for the field remains the central actor in its long life. The fact of this dominance is supported by observation. Ordinary neutron stars of comparable age have faded almost entirely, while magnetars persist as luminous beacons, proving that their interior fields continue to rearrange and release heat. A lesser-known detail is how these fields can shape even the atmosphere clinging tenuously to the surface. In magnetic strengths beyond 100 trillion Gauss, atoms elongate into cylindrical forms, aligning along field lines. This distortion changes the way radiation emerges, producing polarized and anisotropic emission that betrays the hidden order beneath. The light that leaves a magnetar's surface is thus not neutral, but imprinted with the geometry of the field itself. Astronomers reading these signals are reading the architecture of magnetism carved directly into photons. Yet mysteries continue to surround these objects. Among the most enduring is the question of why some magnetars erupt with giant flares, releasing in a fraction of a second the energy the sun emits in 100,000 years, while others with seemingly similar properties remain quiet. Theories invoke differences in hidden toroidal components, variations in crustal thickness, or subtle histories of rotation and progenitor mass. None are conclusive. The uncertainty persists, a reminder that even within strict physics, nature resists simplification. Ironies abound here. The most destructive bursts arise from the most stable structures, fractures born from rigidity, not weakness. The brightest events in the sky come from stars that spend nearly all their time unseen. And the most powerful magnets in the cosmos are also among the rarest, their existence depending on improbable conditions that occur only occasionally. A modern analogy might be drawn to ancient volcanoes. For centuries they stand in silence, their slopes green with time, and then without warning they release energy stored in rock, reshaping their environment in minutes. The magnetar is such a volcano, its eruptions written not in lava but in photons. Over long intervals the magnetosphere continues to evolve. Twists in the field accumulate slowly as the crust shifts beneath, dragging magnetic lines out of alignment. Eventually reconnection occurs, releasing stored energy into the surrounding vacuum. These episodes of magnetic relaxation may be minor, seen only as small X-ray bursts, or vast, visible across galaxies. Yet in either case they are consequences of slow, unseen processes, not of sudden invention. Another quiet effect lies in the interaction between superfluid vortices and superconducting flux tubes. The balance between them influences the rate at which angular momentum is transferred from core to crust. When vortices unpin, they sometimes drag flux tubes, rearranging internal magnetic structure in events that may be linked to observed glitches in rotation. The irony is sharp. Phenomena governed by quantum mechanics on subatomic scales manifest as stellar adjustments seen from across the universe. Mysteries deepen in the broader population. How many magnetars exist in the Milky Way? Estimates suggest thousands, yet only a few dozen are known. Many likely remain hidden, their beams misaligned with Earth, or their activity subdued. This hidden majority suggests that our understanding is partial at best, built on fragments rather than a full census. Three gentle ironies surface. The stars most defined by extremes are among the least observed. The most powerful forces reveal themselves only in silence punctuated by rare noise, and the very processes that sustain their visibility also ensure their slow decline. Observers record spectra and polarization, glitches and bursts, each data point another piece of an unresolved puzzle. Yet the magnetar itself is indifferent to these interpretations. It continues to exist, its processes unfolding at their own pace, immune to the need for narrative. Its life is not a story with beginning, middle, and end, but a condition that persists as long as its field demands. Over still longer spans of time, the field will decay, though not evenly. Reservoirs of energy may remain locked beneath the crust, leaking slowly over tens or hundreds of thousands of years. Some magnetars may transition into quieter neutron stars, their former strength invisible but not erased. Others may remain active far longer, surprising observers with flares long after models predict silence. This diversity ensures that no single fate defines them. The passage of time provides no resolution, only persistence. The spin slows, the crust strains, the field rearranges, the light flickers. Nothing concludes, everything continues. The magnetar embodies contradiction, fragile crust and immense strength, silence and eruption, cooling and heating, decay and persistence. It produces its magnetic fields not once but always, in every adjustment of flux, in every fracture, in every photon. This is its nature, and it endures in patience. The magnetar now resides in an age where its youth is far behind it, yet its power remains evident in the steady X-ray glow and the occasional flare that punctuates long silence. Its rotation has slowed to nearly a dozen seconds, a languid rhythm that underscores the immense torque imposed by its own magnetic field. Despite this deceleration, the field persists as the central force in its existence, maintaining a grip on matter within and light without. The fact of this persistence is observable in the anomalous brightness of magnetars long past their expected cooling age, a brightness that ordinary neutron stars do not share. A lesser-known detail emerges in the possibility that magnetars may shape the very chemistry of their surroundings. The bursts they emit, carrying gamma rays of staggering intensity, can alter the ionization states of interstellar gas far beyond their immediate environment. This effect, though faint at great distance, implies that magnetars do not merely exist in isolation, but influence the galactic medium itself, carving regions of altered ionization that persist after the flare subsides. Such footprints of activity remind us that even a single event can leave long-lasting marks on the galaxy. Yet mysteries continue to deepen. Among the most perplexing is why only a subset of neutron stars cross the threshold into magnetar identity. Some with rapid initial rotation and massive progenitors never reach magnetar fields, while others of less dramatic origin somehow do. The internal processes that decide this outcome are obscured within collapse itself, hidden in seconds we cannot observe. Until more is known, the question remains unresolved, an uncertainty at the core of magnetar physics. Soft ironies settle quietly in this stage. The stars most capable of altering their galactic environment are often unseen until they erupt. The most extreme fields, which deform atoms and polarize light, arise from remnants only a dozen kilometers across, and the very magnetism that grants them longevity also consumes their strength, ensuring their eventual fading. A modern analogy could be drawn to ancient monuments built from stone. They endure for millennia, influencing culture and landscape, yet every year that passes erodes them slightly. The magnetar is such a monument, enduring yet consuming itself in the very act of persistence. The magnetosphere continues its slow evolution. Twists introduced by shifting crustal plates accumulate over centuries, then release in sudden reconnection events. These episodes remind us that the crust is not inert but in dialogue with the field, a dialogue that produces bursts across the electromagnetic spectrum. Observations of soft gamma repeaters and anomalous X-ray pulsars confirm this ongoing interaction, revealing that even in apparent silence the magnetar is never still. Another quiet process unfolds within the core. Superfluid neutrons and superconducting protons, coexisting in a dense equilibrium, interact through pinned vortices and flux tubes. The slow creep of these structures influences rotation and magnetic stability, creating conditions for glitches and for the preservation of hidden toroidal fields. These interactions are quantum mechanical in origin yet cosmic in consequence, linking the smallest scales of physics with the larger scales of astrophysics. The irony rests in the disproportion. Subatomic behaviors govern stars whose influence reaches across galaxies. Mysteries grow in the context of their population. If thousands of magnetars exist in the Milky Way, why are so few observed? Perhaps their emission beams miss Earth. Perhaps most remain in quiet phases, their bursts rare. Or perhaps the true magnetar phase is briefer than imagined, lasting only tens of thousands of years before decay dims them. The lack of certainty ensures that each known magnetar is a rare insight into a larger unseen population. Three ironies emerge again. The universe hides its strongest magnets in silence rather than spectacle. The most violent flares occur so rarely that lifetimes can pass without them, and the most extreme states of matter, impossible to create on Earth, are common inside these small, obscure stars. The magnetar endures regardless of what is known or unknown. Its spin continues to slow, though asymptotically. Its field continues to rearrange, though ever more gradually. Its crust continues to strain, though with less frequency of fracture. Yet the processes remain unending, never resolving into conclusion. There is no final act, only persistence. Over still longer spans of time, the star may cool further, its surface temperature dropping while its field slowly decays. Yet even then, hidden reservoirs of magnetic energy may linger, producing occasional bursts that surprise observers. This unpredictability is part of the magnetar's essence. It resists categorization, existing not as a single event but as an ongoing state that redefines itself continually. The magnetar produces its powerful fields not as an echo of collapse alone, but as an active and enduring condition woven into every layer of its existence. It is not a story told once, but a presence that continues, a balance of forces that refuses closure. In silence and persistence, in contradictions and mysteries, the magnetar turns slowly on, carrying its strength through ages indifferent to human measures of time. The magnetar enters a phase where its life is measured not by centuries but by tens of millennia, and yet its presence remains unmistakable. Its spin now drifts at nearly a dozen seconds per rotation, a rhythm that feels glacial compared to its violent birth, but the magnetic field still dominates its structure and behavior. The fact that this field remains so strong is confirmed by the continued emission of X-rays, far brighter than that of ordinary neutron stars of comparable age. Even when no flares erupt, magnetars shine stubbornly, proving that their magnetic interiors are never at rest. A lesser-known detail of this stage is how the immense field sculpts particle populations around the star. Electrons and positrons are created spontaneously by the field itself, their existence made possible because the magnetic intensity exceeds the threshold at which vacuum becomes unstable. These particles, constrained to spiral along field lines, generate a persistent halo of emission. The magnetosphere, far from being empty, is thus alive with pairs, a plasma born not of heat but of pure magnetism. Yet mysteries refuse to yield. One of the most enduring questions is how long such fields can persist. Calculations of resistive decay suggest lifetimes shorter than observed, while models of flux tube and vortex interactions hint at longer endurance. The true answer remains elusive, concealed within physics that cannot be tested on Earth. Do magnetars remain magnetically active for hundreds of thousands of years, or do they fade more quickly into ordinary neutron stars? Observations offer fragments, but no certainty. Soft ironies settle gently into this uncertainty. The strongest fields known in the universe cannot be measured directly, but only inferred from faint pulses of light. The very stars that glow with extraordinary brightness remain rare and difficult to find, and the processes that ensure their persistence also guarantee their eventual fading. A modern analogy suggests itself in ancient trees. Their immense strength is visible in their size and endurance, yet each year consumes them a little, and in their growth is also their slow decline. The magnetar is such a tree, its field both sustaining and eroding it. Over these long ages, the magnetosphere continues to twist and release. Stress in the crust shifts magnetic footpoints, altering the structure of the external field. At times, the rearrangement is quiet, manifesting as subtle changes in pulse profiles or polarization. At other times, it is violent, producing bursts of X-rays and gamma rays that can be detected across galaxies. These events are not predictable, and their irregularity ensures that magnetars remain enigmatic. They do not follow schedules, they follow physics that resists simplification. Another quiet process is the gradual cooling of the core. Neutrino emission declines, photon cooling dominates, and temperatures fall. Yet resistive decay of magnetic knots continues to inject heat into the crust, maintaining surface temperatures higher than models predict. This paradox is well documented. Magnetars remain hotter than expected because their fields themselves are sources of heat. The contradiction is not resolved. It is accepted as truth. Irony rests in this duality. The fields that should decay are also the reason decay is delayed. The cooling that should silence the star is offset by heating that ensures it continues to shine. And the very rigidity of the crust that provides stability ensures fractures that destabilize it. Mysteries also remain in the diversity of behavior. Some magnetars flare repeatedly in short intervals, while others remain quiescent for centuries. The causes are uncertain, Variations in magnetic geometry, differences in internal structure, or hidden reservoirs of toroidal fields may play roles, but the evidence is incomplete. Each magnetar is unique, and their individuality resists generalization. The spin continues to slow, yet never halts. The field continues to drift, yet never vanishes. The crust continues to strain, yet never collapses entirely. In this stage, the magnetar embodies endurance without resolution, persistence without closure. It does not move toward conclusion, but remains in balance between processes that never finish. 3 more ironies appear here. The stars that reveal physics beyond laboratories do so only rarely, leaving us to infer from fragments. The most extreme conditions in nature produce not clarity, but diversity, and the objects that embody contradiction endure far longer than expected. The magnetar persists in silence, glowing faintly but steadily, turning slowly, shaping its environment in subtle ways, and embodying contradictions that remain unresolved. Its field is not simply a remnant of collapse, but an active presence that continues to define its existence. In the deep quiet of space, the magnetar is not dramatic but patient, a condition that stretches across time without seeking resolution, indifferent to whether it is seen or understood. The magnetar drifts into ages when its bursts have become less frequent, but its presence remains unmistakable through the steady pulse of X-rays that leak from its surface and the faint polarization of light that passes near it. Its spin, now counted in intervals of many seconds, measures the passage of time not as motion but as loss. For every additional moment added to its rotation is energy surrendered to the field that surrounds it. The fact of this slow rotation is one of the simplest observations of magnetars, yet it speaks volumes, for no other neutron stars decelerate so quickly or reach such languid rhythms so early in their lives. The magnetic field that defines them remains the only explanation. A lesser-known detail of this stage is the subtle effect of starquakes on the surrounding plasma. When the crust fractures, it launches alpha waves into the magnetosphere, twisting and accelerating particles. These waves ripple outward like unseen tides, disturbing the plasma environment for days, long after the initial burst has faded from detectors. Such lingering echoes confirm that the magnetar is not a star alone, but a system in continual conversation between interior and exterior, crust and magnetosphere, fracture and wave. Yet mysteries remain unresolved. Chief among them is the fate of the toroidal fields believed to slumber within. Some models suggest that these hidden reservoirs decay only slowly, leaking energy over hundreds of thousands of years, while others argue for more rapid loss. Observations do not yet decide the question, for the timescales extend beyond human record. Do magnetars fade quietly into obscurity, indistinguishable from ordinary neutron stars, or do they carry remnants of magnetism long after their visible signs have vanished? The answer remains hidden, and the uncertainty defines our understanding as much as the facts do. Irony rests in this hiddenness. The strongest magnetic fields known cannot be measured directly, but only through indirect consequences. The most extreme stars, carrying physics beyond terrestrial reach, conceal their true nature beneath layers of silence. And the very processes that produce bursts are also the ones that ensure centuries of quiet, leaving observers with long waits between revelations. A modern analogy could be drawn to earthquakes along a fault line. Most of the time the ground is still, the strain invisible, and then in a sudden instant the energy releases. Between quakes the silence is deceptive, yet it is the silence that holds the story. The magnetar lives by the same rhythm, its stillness filled with hidden motion. Over spans of many millennia the magnetosphere also evolves, losing energy through reconnection and radiation, but continually replenished by stresses from the crust. This slow breathing ensures that even in advanced ages magnetars can produce bursts, though less frequently than before. Their environments remain active, alive with pairs of particles generated spontaneously by the strength of the field. These particles, spiraling along magnetic lines, sustain a faint glow that makes magnetars visible long after ordinary neutron stars vanish into quiet. Another subtle feature is the deformation of the star itself. The field is strong enough to distort its shape slightly, pulling it away from perfect sphericity. Such distortions, though small, may generate continuous gravitational waves as the star spins, signals faint but potentially detectable with sensitive instruments. If ever confirmed, these waves would provide another window into the unseen structure of magnetars. The irony lies in scale. The smallest of deformations, imperceptible in human terms, could generate ripples in space-time itself. Mysteries deepen in their diversity. Some magnetars live briefly, their activity fading after only a few thousand years, while others persist far longer. The reasons remain unclear, hidden in the subtleties of birth and evolution. Perhaps rapid initial spin amplifies fields that last longer. Perhaps internal composition differs. No theory yet captures the range of behavior observed. The uncertainty remains as much a part of magnetars as their fields. Three more ironies lie softly here. The most luminous bursts are followed by the longest silences. The strongest magnets are among the hardest to find, and the stars that seem most alien in their physics are still born of processes familiar: collapse, rotation, matter, and field. The magnetar persists regardless. It does not resolve its contradictions, nor does it conclude its processes. It continues to spin slowly, to emit faintly, to strain and to release in cycles without end. It exists not as a story with conclusion, but as a condition, a dialogue between matter and magnetism that does not finish. The magnetar produces its fields not once but always, in every adjustment, every fracture, every photon. It is not a remnant but an active presence, an object that endures far longer than human time can measure, carrying within it contradictions that remain unresolved and power that remains immense. In the deep silence of space, the magnetar turns on, indifferent to observation, yet shaping its environment with every moment of its existence. The magnetar continues into eras so extended that human history is a flicker beside them, yet its identity remains bound to the magnetic field that defines it. Its rotation has slowed to more than 10 seconds, its pulses faint compared to their youth, but the star still glows in X-rays, proof that its field continues to release energy. The fact that magnetars remain hotter and brighter than ordinary neutron stars of similar age is one of the most compelling confirmations of the role magnetic decay plays in sustaining them. This persistence is not theoretical, but observed across multiple sources, each one defying cooling models by radiating more strongly than expected. A lesser-known detail of this age is the possibility that magnetars contribute to phenomena beyond their own immediate emission. Some astrophysicists have proposed links between magnetar flares and fast radio bursts, millisecond flashes of radio waves detected from across the cosmos. Though the connection remains uncertain, the timing and energy scales are suggestive. If true, it would mean that magnetars influence not only their local environment, but also transient phenomena visible across the universe, their magnetic reconnections echoing in frequencies far from their origin. Yet mysteries deepen. Do all magnetars eventually contribute to such bursts, or is this capacity restricted to a rare subset? The lack of consensus reflects the difficulty of connecting events observed fleetingly on Earth to processes hidden deep within stellar interiors. The question remains open, an uncertainty that adds to the aura of magnetars rather than diminishes it. Three ironies rest here. The smallest stars in size produce bursts that rival galaxies in brilliance. The most extreme processes leave the faintest trails, requiring immense effort to detect, and the very stars that illuminate theories of high-energy physics are also those most reluctant to reveal their secrets consistently. A modern analogy lies in the deep ocean, where bioluminescent creatures flare briefly in darkness, revealing themselves for instants before vanishing again. The magnetar, too, glows in brief displays whose origins remain half hidden. Over millennia, the magnetosphere continues to evolve. The slow creep of magnetic stresses in the crust displaces field lines, gradually twisting the external structure. At times, these changes are minor, altering only the polarization or spectral features of the emission. At other times, they accumulate to thresholds that unleash flares powerful enough to be detected across intergalactic space. The cycle of stress and release continues, not as drama but as inevitability, a physics that neither hastens nor delays but proceeds at its own pace. Another subtle process is the interaction of the field with the surrounding interstellar medium. As the magnetar drifts through space, its magnetic wind carves a cavity, altering local plasma and leaving behind traces detectable in X-ray or radio signatures. These marks are reminders that magnetars do not exist in isolation but shape the galaxy around them, writing their presence even where they are not directly seen. The irony here is clear. The most isolated of stars leave the widest footprints. Mysteries persist in the long-term evolution of their fields. Some magnetars exhibit sudden declines in emission, fading more quickly than models predict, while others sustain activity much longer. The cause of this divergence is unknown. Perhaps hidden toroidal fields prolong activity, perhaps initial conditions differ, perhaps stochastic processes within the crust dictate the outcome. Whatever the cause, the diversity of behavior resists a single explanation. The magnetar population is not uniform but scattered across a spectrum of outcomes. Three ironies settle gently again. The most extreme conditions produce the widest diversity of behavior. The strongest magnetic fields do not guarantee identical lifespans, and the stars that embody power also embody unpredictability. The magnetar persists nevertheless. Its spin continues to slow, its crust continues to strain, its field continues to rearrange. Nothing resolves, nothing concludes. Processes overlap, contradictions endure. Cooling is offset by heating, silence is interrupted by bursts. Fragility coexists with resilience. The star remains what it has always been. A dialogue between collapse and persistence, between matter and magnetism, between silence and eruption. Over still longer spans of time, the magnetar will gradually fade. Its field will decay, its luminosity diminish, its bursts grow rarer. Yet even in decline, it remains distinct, carrying traces of the field that once defined it. Whether it ends as an ordinary neutron star or as something subtler is uncertain. The universe keeps that secret, and human lifetimes are too brief to learn it. The magnetar continues, indifferent to observation, indifferent to conclusion. It exists as condition, not as story. It produces its fields not once but always, each photon and each fracture another expression of its persistence. In the quiet of space, the magnetar endures, a monument of contradiction, and a reminder that the universe holds mysteries that will never be resolved in full. The magnetar drifts into the far reaches of its life, its rotation having slowed to long intervals that seem more like pauses than pulses. Its surface cools steadily, though never as fully as ordinary neutron stars of similar age, for its field continues to inject heat from within. The fact that magnetars remain brighter than expected long after their formation is among the strongest pieces of evidence that magnetic decay is an active process rather than a static inheritance. This persistent glow, though faint compared to their earlier outbursts, ensures that they remain visible to sensitive instruments for tens of thousands of years. A lesser-known detail is the way the crust continues to store stress long after the major quakes have subsided. Even when the star seems quiet, microfractures ripple beneath the surface, releasing heat that seeps outward. These small shifts do not register as flares but contribute to the steady luminosity that distinguishes magnetars from their quieter kin. Such hidden motions remind us that even silence is full of activity. Yet mysteries remain unresolved. One of the greatest is the final fate of magnetars. Do they eventually lose enough magnetic strength to become indistinguishable from ordinary neutron stars, their unique identity erased by time? Or do they retain some hidden remnant of their former power, fields buried deep within that never fully fade? Theoretical models offer different answers, but none is certain. The timescales are simply too vast, the data too limited. This uncertainty persists like a question carved into stone, waiting for an answer that may never arrive. 3 ironies mark this closing stage. The stars that once shouted with bursts across galaxies now whisper in faint light. The strongest fields in nature end not with a final display but with slow surrender. And the objects that challenge theory most intensely eventually fade into obscurity, blending into a population of remnants barely noticed. A modern analogy could be drawn to a fire forged in violence that burns brightly at first, then settles into embers that glow long after the flames are gone. The magnetar is such a fire, its embers lasting millennia, its heat sustained by processes deep inside. Over spans longer than human civilizations, the magnetosphere weakens, its structure simplifying as reconnections exhaust their reservoirs. The once tangled field becomes more dipolar, less twisted, less prone to flare. Bursts become rare, then cease. The magnetar does not die in a single moment but recedes gradually, its extremity mellowed by time. Another quiet process continues within. The interaction of superfluid vortices and superconducting flux tubes slows, their dynamics less influential as energy dwindles. The crust becomes more stable, its fractures smaller, its capacity for giant quakes diminished. Yet even here, faint activity may linger, reminders that magnetism never fully rests. The irony is soft but striking. The processes that once drove violence persist even as the energy to fuel them fades. Mysteries remain in whether such aged magnetars can still affect their surroundings. Some argue that their past flares may seed structures in the interstellar medium that outlast the stars themselves. Others suggest that even faint fields may influence nearby plasma flows. The extent of these legacies is unknown, but the possibility adds to the quiet weight of their influence. 3 final ironies present themselves. The stars that seemed eternal in their power are subject to decay like all else. The most extreme states of matter eventually return to quiet forms, and the objects that defied understanding may leave no trace other than faint embers in the sky. The magnetar's story is not one of climax and resolution, but of endurance and fading. It produces its fields not in an instant, but across ages, sustaining them through contradictions, releasing them in bursts and surrendering them in silence. Its life is a condition, not a narrative, a balance between gravity, quantum matter, and magnetism that never truly concludes. In the end, if N can be said to exist, the magnetar becomes ordinary, its uniqueness hidden, its brilliance dimmed. Yet for as long as it endures, it remains one of the universe's most profound expressions of physics pushed to its limits. It is a reminder that the cosmos is shaped not by drama, but by persistence, not by resolution, but by continuity. The Magnetar does not end with a final act. It simply continues until it no longer can, carrying its contradictions into the silence of time,